We will now continue with the presentation of Rodrigo Braga from Siemens Germany, global business developer for the distribution network, who will talk about how to guarantee the continuity of the electrical supply using the automation process. Rodrigo, thank you very much for being with us today. Welcome to Siemens Mineral Week. Hello, good afternoon. Thank you for being with us. Rodrigo, we will have around 15 to 20 minutes for your presentation, then space for questions, and the questions will be in English, of course. So you already have the microphone available to start your presentation. Thank you very much. I will continue in English.
Thank you for the introduction and a warm welcome also from my side. As presented, I would like to talk about to guarantee the continuity of power supply through grid edge automation, especially applied to the mining industry, which is our topic today. I'm Rodrigo Braga. I'm an electrical engineer working as a technical sales consultant for energy automation systems at Siemens Smart Infrastructure Digital Grid. Just to give you a bit of a background, my expertise is in feeder automation, and during the last years, I have been involved in several projects worldwide, working closely with electrical utilities and different vertical industries. So in this session, I would like to talk about new system approaches relevant to electrical infrastructure applied to industrial environments, specifically the mining industry. Specifically here, the different cases supported by the protection relays, or as you will see, our grid edge devices, and their main benefits, especially when you understand that their main objective is to secure and protect the power supply of the industrial process. And that's exactly the question that will lead us through this presentation. So when looking at the industrial process, how to protect and secure power supply? First, let's have a look into the main challenges. So on one side, protect critical loads from power interruptions, avoid overload scenarios, reduce outage size and duration whenever there is an outage out there, locate faults faster, and ideally, if we can optimize our operational expenditures, by reducing the crew size to isolate and restore the systems. I would say these are the main goals when we search for such intelligent automation. Well, let's take a short look now into a typical single line diagram of a mining industry. So we have on the top the so-called primary station, high voltage to medium voltage, supporting a redundant grid in-feed connection to the facility. You can see here from the example. Where in the first instance, I would say the reliability of the system is supported by the energy supplier, in this case, the TSO or the DSO. Going down in the electrical grid structure, we see now what we call a ring or loop configuration connected to the primary substation. I think it's also clear when we hear in the picture, here loop structure connected to the primary substation. In this diagram, the loop consists of 3 secondary stages. See it here, where both circuit breakers connecting the loop into the primary substation are closed. Normally, we have here so-called normally open point. Yeah, sorry when I move a bit my head, but I'm also looking here to the slide so that I can also follow the presentation. And let's say along the loop, we have also, as I was mentioning, the normally open point. That normally open point is in fact very relevant, as it may support required loop reconfiguration on field level. Finally, connected on that loop through the secondary stations, in some cases mobile containers, as per the picture left. See here a representation of a mobile station. We have connected then in that loop, several different types of critical loads. Whether we have electrical shovels and drills, mining machinery, water pumps, and other critical process, as we can see here from the picture, where I would say a fault on the system can lead to a power outage, and in case a contingency plan is not in place, as a consequence, to a production stop that can go from minutes to several hours. And we also know that monetary losses can skyrocket very quickly for an unproductive minute out there. So how can we improve the overall system reliability in order, let's say, to maintain the power supply once in the presence of a power outage and still be able to protect and secure those critical loads? Well, I think we have already partially answered this question by just looking into this simple or single line diagram. The first aspect, maintaining a redundant grid topology based on the loop structure, as in the example presented. I would say with such approach, we are supporting the redundant supply of loads and also allowing, let's say, full flexibility to connect and disconnect loads, for example, in the case of maintenance works. But I would say that's just one part of the answer, yeah, at the end of the day. Looking at the technology available today, namely the grid edge automation, interesting is, in fact, what can be implemented on the loop as part of the so-called high-speed self-healing algorithms and grid reconfiguration without any intervention of the network or system operator. Let's look into the working principles of such technology. Well, if we start here with a picture on the right-hand side, I would say, or I would start to explain a bit the system architecture we see here. The main principle relates first to the possibility to have in place a so-called decentralized system architecture, where intelligent devices controlling the local breakers can communicate between each other on a peer-to-peer basis without the intervention of a central SCADA. This means that the system can automatically react to an outage or overload event without requiring the intervention of the network or the SCADA operator. For this purpose, as you can see also here from the picture, a communication network is set up in accordance with the state-of-the-art IEC 61850, a communication standard for energy automation. Supported by the standard, and that's also a very, I would say, relevant service or feature that the standard supports, a field device can multicast messages to all the other devices present in the same network, allowing them, therefore, to decide whether or not to discard its content. The main advantage relates specifically to the speed of that communication and the reliability of the automation process. That's, I think, one important part of the system implementation. So we have this so-called decentralized architecture. We have 61850 in the middle supporting horizontal communication, or let's say communication straight away from field level. And last but not least, I would like also to bring into the picture a specially designed algorithm implemented on the grid edge devices, so-called JDIF algorithm, which in essence analyzes the fluctuations of current on the different sections of the loop and decides on the appropriate grid reconfiguration. So you can imagine at the end of the day, we can react in a much faster way without being that dependent on latency times of communication from field device to station level, DCS, and let's say waiting for the feedback of the central SCADA in order to react on required grid reconfigurations. So that's a bit the principle. If I can sum up the main ideas, now I would also like to take a look into the main application cases that such architectures can support. So the first one, fault and outage management, automated switching for isolation and service restoration. So more commonly self-healing as a concept, let's say, more commonly known. Well, let's take a look here into the picture. We have again a representation of the loop structure. So you can see here from the top of the picture, we have let's say 2 wind feeds from the primary substation, and then they are interconnected through the presence of this normally open point. Along with criticals which are connected to these different nodes. They can be, let's say, medium voltage stations or even pole top installations like reclosers, breakers, disconnectors, but that all, let's say, behind critical load, which has to be supplied, secured, and protected at the end of the day. So what will happen in face of a fault, in presence of fault, normally on the traditional schemas, let's say operating schemas, most likely I would be, if I have, let's say, a circuit breaker at the head of the feeder, I would have the entire feeder disconnected, and I would be basically losing all the critical loads connected in that specific feeder. So this is what we want to avoid, because as discussed before, we want to be able to reconfigure immediately the loop once in the presence of a fault. And again, we know that every minute counts. So how the system operates, again, based on this IC61850, as you can see here on the bottom of the screen, all these devices, these grid devices installed on these different stations, they are basically interfacing between each other, multicasting so-called goose messages, and informing about the grid status. Once this information is allocated to the different nodes, we are in functions to properly isolate the position, as you can see here. So we have here two open to isolate that session, and finally we can restore the power supply to the non-affected grid areas or loop sections. So you can see again, my system can still operate. In average, let's say we are running, or the system runs the whole operation, the loop automation, in less than 300, 200 milliseconds, depending a bit on the project-specific details. But at the end, if I have, my motivation is basically to isolate the loop as fast as possible and still being able to operate remaining areas of my installation. Well, that's in essence the concept of decentralized automation. I would also like to approach the topic with a second and relevant application case, which is called load management. So with the same devices, we can support the so-called automated switching for dynamic reconfiguration. Well, the same principle applies. In this case, again, I have my loop structure. So you see the importance also of having a grid with a physical redundancy that supports the rollout of such technology. And at the end of the day, what we want, again, based on the intelligent grid edge devices, which are installed along the loop, the possibility to, on real time, detect the load profile of these nodes along the loop structure. You can see here from the picture, from the example, I have station or in-feed A supplying loads to normally open, and the same here from the in-feed B pouring those down from this side. So currently we have the information from the field, from the device, that there is less load here on the left. Maybe I don't have so much let's say mining machinery operating at that point of the day or the time, let's say, and I'm running some kind of overload in this particular part of the loop section. So again, what are the devices looking to perform? To stabilize the load through the entire grid structure or infrastructure, and again, by shifting the position of this normally open point here from this, let's say from the middle of the loop, close now to the in-feed point B, you see I'm immediately reducing the loads coming from the right-hand side, reducing then the potential overload scenario, and safely increasing the loads coming from in source A, and therefore assuring it of the day in a dynamic way without any intervention of a SCADA operator that the grid is properly stabilized. So these are two relevant application cases when we talk about grid edge automation that on one side allow us to protect and secure the loads from outage events, and secondly, also protects the system from any overload situation, overload event. Well, if we move now a bit into the next slide, the intention is again to make it clear, let's say, as per opposition to a centralized architecture, in such setup, as you have seen so far, the whole process of decision takes place at field level. So very close to the industrial process itself. That's important, and the next slide tries to make it a bit more clear. We are mainly talking here about a decentralized automation schema That implies, of course, a decentralized architecture. And let's understand a bit the different benefits and advantages from such architectures. So this is exactly what I try to put in perspective in this table. Okay, we start here on the top from, I would say, a more conventional system architecture, where we have traditional centralized architecture, where the control center, or SCADA, is responsible to operate for operating the entire industrial process, but also the electrical infrastructure. And then while we go down, basically what we are seeing is the possibility to cascade down the logics, the control hierarchies from the SCADA, from the control center, down to the field or to the grid edge devices. And that's exactly where we ended up here on the field level. And at this point in time, what we see also, if we understand a bit here from the right-hand side, is that on one side, we are decreasing complexity if we go down, because basically from the implementation point of view, we don't have to aggregate that much amount of data on the control center, because anyway, we are looking for a specific area of my compound, of my industry. And at the end of the day, I'm improving on the decision time. So I'm optimizing the decision time from, let's say, some seconds to some milliseconds, or in some cases to some microseconds. Yeah, that's the main benefits. Those are the main benefits, I would say, I would like to put in perspective. So decreasing the complexity of system integration, but also optimizing on the decision time. Yeah, then I think an important aspect to bring into a picture is the communication infrastructure. It's, of course, highly dependent, such architectures, on the performing communication infrastructure. So in that sense, when installing such solutions, communication is one of the key elements for success. In many cases, the industries have their own communication infrastructure already in place, and depending on the architecture type and the application main requirements, different communication technologies can be considered. Let's take a look here in the next example, because that also brings us a bit into perspective what are the main aspects when we consider such solutions. So while cellular 4G is already out there and certainly better than 3G from a technology point of view, still has a higher OPEX, or operational expenditures costs, and therefore not so deeply dispersed for such type of applications, I would say. That's one motivation. A second motivation is that in many cases, yeah, the installations, they will be in remote areas where even cellular coverage maybe is not there, correct? So again, there is a need for considering alternatives. WiMAX, on the other hand, with its higher bandwidth and longer reach, can be used for such time-critical applications, providing a trustful and reliable communication link. This slide represents a typical installation on the loop network. So the single line diagram at the bottom of the graphic shows two substation sources on a loop feeder with an open tie, a normally open point. In this example, the grid edge automation employs the state-of-the-art communication standard in electrical world, what we have just saw previously, so the IEC 62850, for all operational and non-operational data exchange among these devices. In the diagram, the communication media is supported by the WiMAX radios, as you can see here from the picture. Yeah, this is to allow you a bit of, or a comprehensive view over the system architecture, but I would like still to bring some other considerations regarding communication. Yeah, and here again some other examples from a project where we have implemented a similar architecture, where again that was a highly area. So still running cellular communication would still be highly costly for the let's say for the industrial area, and therefore there was a need for us to consider preliminary planning due to the difficulties of the terrain. So a telecommunication pole of 70 meters high to achieve direct optical visibility was required, because normally this technology works in line of sight. As you may know while using such technologies. And here we haven't used WiMAX specifically, but we have used similar technology, microwave technology, also based on radio equipment with a frequency range of 5 gigahertz. Point-to-point and point-to-multipoint links were established to cover, let's say, the given area, hilly terrain, so mountains were in the middle, and testing on all locations to ensure that the links would have enough throughput of 25 megabits per second and a high reliability plus low latency for communication. Antennas were located at 8 meters high on the poles. Yeah, so very close in this case to recloser controllers. But again, I think important here to highlight is that the flexibility for such architectures is there. So whether we are supporting overhead line systems or cable grids, underground cable grids, at the end doesn't really matter. Because what we really want to pursue is the system architecture type and the possibility to install such devices on the field. Well, just to summarize, I would conclude basically saying that grid edge devices are there to support such type of applications for secure and efficient network operation. And if we summarize on the benefits, so they are mainly there to prevent power outages, protection of primary equipment from damage. So as we can combine the protection functions with the automation, we have everything in one single device. Decentralized automation for mission critical operations, specifically for this domain, as we want to reduce time latency of communication and we want to act fast because we know that every minute counts. This is the main motivation. So faster grid operation and reconfiguration at the end of the day. And as we have seen also the possibility to avoid overload scenarios. So that's in a nutshell what I would like to bring for today's presentation. I hope I have completed the presentation within the time expected. And thank you once again for your attention during this presentation. I remain available for questions if there are some. Thank you.